Hi, I'm Princess Senate Conference producer at Technology Networks, and I am here to introduce our final talk of day one, Phantom Metabolites, Unraveling Metabolic Shadows. I am pleased to welcome our speaker, Dr. Gary Siuzdak, a renowned expert in metabolomics and mass spectrometry. So Dr. Siuzdak is a professor and senior director at the Scripps Center for Metabolomics and Mass Spectrometry. So with over 300 publications and a focus on innovative techniques, Dr. Siuzak's work is advancing the field. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And without further ado, I will now hand over to Gary to begin his presentation.
Okay, well, thank you, Princess, and thank you, Technology Networks, for this opportunity to talk about some very recent work that we've been involved with here at Scripps, and also some work that we haven't yet published. So there's been a lot of discussion in the past year or the past couple of years about the dark metabolome and unraveling the mystery behind all these peaks that we're observing in metabolomics and lipidomic experiments. And I'm going to give you at least the results of our efforts in this area. And basically, in this relatively short presentation, it'll come down to one primary message concerning the metabolome and the lipidome, and also a potential solution to that, to this primary issue associated with the metabolome and lipidome. So in the end, there'll only be one thing to remember, I think, as a simple message. I typically describe what I do as metabolomics, but I've always, at least in my mind, included lipids in that idea of what I do. However, the field of lipidomics is gradually become a more distinct field from metabolomics. So I like to now say that we do both metabolomics and lipidomics. In fact, we recently did an assessment of what our lab does, and the majority of what we do is actually lipidomics. So where we have a focus on any sort of metabolites, be it central carbon metabolism or lipid metabolism, it really doesn't matter. We're interested in these small molecules and specifically how they can impact physiology. But that's not something I'm going to talk about today. What I'm going to talk to you about today is our primary platform and how we've been using that platform. So our primary platform, which I think is very similar to most of the individuals out there, basically we do LC-MS analysis on molecules that we're interested in, and then we do a statistical assessment of the any comparative analysis and try to pull out the peaks that are most interesting. After we find these peaks that are most interesting, we then assess and our platform at XCMS is the statistical assessment software. And within this platform, we also have the MS-MS data, or the tandem mass spectrometry data. And that information is used to do the molecular identification. And we now have integrated within XCMS our METLIN database, which is a database of currently 936,000 molecular standards, each with MS-MS data at multiple collision energies. So the issue at hand, and one that a lot of individuals have focused a great deal of energy on, is when we do this sort of experiment, a lot of the molecules that are being observed, or a lot of the peaks that are being observed and assessed by MS-MS analysis, are unidentifiable within any of the databases. And that's come to be known as the dark metabolome or the dark lipidome. So these molecules that are unidentifiable are typically characterized as the dark metabolome. And by many assessments, actually not just a couple, but quite a few assessments, that people have talked about millions of molecules not being identifiable, and that the metabolome and lipidome are only currently known to less than 10% of what's actually been previously identified. So we actually went about this in a fairly systematic way to assess the different technologies that are being used to look at the metabolomic and lipidomic experiments. The first thing we questioned or asked about is how reliable or how good is the tandem mass spectrometry data that we're looking at, and could that be a potential source of the issues that we're facing? A second question is a common technology that we actually developed in 2008 called similarity searching. How good is that? Is that a solid technology for identifying these molecules? A third is something that we also have been very much involved with, is in silico-based identification of the MSMS data to provide structural information. And the fourth part of this has been the question of how much of an impact is in-source fragmentation playing in the analysis of these peaks, or the analysis of, or the confounding nature of these peaks that we're observing. Okay, so first off, the tandem mass spectrometry data, how reliable is it? There's lots of different platforms out there, and from Agilent, Waters, Bruker, Thermo, SciEx, and others, Shimadzu. So what we did was we went about it very systematically and looked at, and fortunately we have these instruments that are shown here all in our lab. So we have Agilent, Bruker, SciEx, Thermo, Waters, and these five instruments. And what we wanted to get a sense of was how reliable was the tandem mass spectrometry across these different platforms. So we looked at we took our Metlin database, which is composed of MSMS data, as I mentioned earlier, at 4 different collision energies, and we compared that data, which we generated off the Agilent QTOF instrument, and we compared that to the Thermo Q Exactive, to a SciEx QTOF instrument, or triple TOF as they call it, and also to the Waters QTOF instrument, SYNAPT 2, and also the Bruker Compact 2. And the results that we got were actually, I think, I'd like to say they were surprising, but in reality, they weren't surprising. It's something that we have noticed, at least on a just a regular basis, when we visually compared the data across instruments. They tended to be actually quite good in terms of how well they compared, and that's basically what we found here. So the primary difference between the instruments was not in which fragment ion was showing up. That was actually extremely consistent. Instead, what we found was that the intensities could vary across the different collision energies. But overall, the fragments that we observed were very consistent, and we did see, like, the most variation perhaps came from the Waters, but again, the ions, the fragment ions, were the same. It was primarily just in some of their intensities that varied a little bit. And this was true across many different molecules. We looked at a total of about 50 molecules, I believe, in this study, and we got highly consistent results across all of them. Actually, it was closer to 100 molecules, I'm sorry. And when we did again, just running through these fairly rapidly, but it's the reason I'm running through them rapidly is because the results are fairly boring. They're actually very consistent. Here's a kind of an overview assessment of what we were observing in terms of the cosine scores. Here you can see the collision energy on the x-axis and cosine score on the y-axis, and the scores were generally above 0.9, and the consistency was really quite high between all of the different instruments. And this was as compared to the Agilent instrumentation. And we also were able to do an assessment of consistency across the cosine score across the number of fragment ions that we're observing in these MSMS experiments. And again, you can see here the consistency was quite high. The highest consistency typically was when we had between 1 and 10 fragment ions. But again, very high consistency. And overall, when we did an assessment of the number of the different collision energies and compared the different platforms, what we found was that 20 electron volts was the most consistent platform in terms of generating the most reliable data across the different instrument platforms. So with that, what I can easily say is that tandem mass spectrometry data is very reliable across these instrument platforms. So I wouldn't say this has anything to do with the source of so many molecules not being able to be identified using current tandem mass spectrometry databases. Similarity searching, this is one that I've always been quite excited about this, and I've been excited about it simply because we came out with the first paper on this technology back in 2008, and I was always quite bullish about it. I always thought it was a great technology that would allow you to get perform simple analysis of molecules that weren't in the databases, in the tandem mass spectrometry databases, and help you determine what they were similar to in terms of structural similarity. To me, that made perfect sense. If the tandem mass spectrometry data was similar, you'd expect to have a very similar structure. At least that was the idea. It was, and my evidence for that was extremely anecdotal at the time, and so what we finally decided to do over the last couple of years was look at this a little bit more seriously and see if in general, if the anecdotal information stood up to actually looking at large sets of molecules. And in my case, I personally went through about 200 molecules, looking at structural analogs between these molecules to see how well or how similar these molecules were in terms of their tandem mass spectrometry data. And I'll just give you a quick sampling of that. And we also not only looked at tandem mass spectrometry data, but we also looked at the neutral loss mass spectral data as well. So we created a database of our own in Metlin, which is called Metlin Neutral Loss. And that basically what is derived from the MSMS data. And so we looked at both types of data, MSMS and neutral loss data, to see what kind of similarity there was or how strong the similarity was between very similar structures. And like what I'm going to do right now is just give you a snapshot of what I observed. So here was a molecule that is extremely similar. This is a molecule by Jean-Marie Galano. He had synthesized these molecules and he provided them to us for the Metlin database. And they're structurally very similar, except one has as you can see, a hydroxyl group on the bottom, and the other one in place of that has a ketone. Besides that, they are identical. However, when you look at the tandem mass spectrometry data, it is very, very different. In fact, the only ion there that is similar is the ion at an M/Z of 71. And it's obviously a fairly significant difference between these two spectra when you consider how similar the structures are. Here's another example of this. This is a statin molecule that I've analyzed, and this was, again, the structure is completely identical between these two, except for a methyl group here versus a hydrogen atom here. And if you look at the tandem mass spectrometry data, the only overlap or similarity between these are the ions at 300, 258, and 133. So the similarity is at best poor, and I certainly would be hard-pressed given this sort of information to, one, say they were similar, and two, to actually make an identification of the other molecule. And the last one I'll show is these two molecules, dimethylsphingosine and sphingosine C20. Again, very similar molecules in terms of structural information, and here the overlap is only 3 molecules. So I think the point I'm trying to make here is that if you're trying to use, when we typically do identifications, the things that we our go-tos in terms of identifications are usually very simply the retention time to make sure that those match. The second is accurate mass measurements. And the third is MSMS data. So if you're only relying on similarity between one spectra and another, I'm afraid, at least, and I'm kind of sorry to say this because I was hoping, based on the fact that we came up with this similarity searching originally, that it would be much more powerful than it actually is. So the bottom line, at least for us, is that we do not use similarity searching for any real structural annotation, simply because of its lack of reliability. We've also, very early on, about 6 years ago or so, were early adopters in silico identification of molecules, basically trying to use tandem mass spectrometry to identify molecules, and in the reverse, taking the structure of the molecules and generating tandem mass spectrometry to generating the tandem mass spectra from those structures. The one thing that we learned early on when we actually put that data into the Metlin database initially was that the users found it to be very unreliable. The overwhelming feedback was that it was not helping in terms of the identification process. This has actually become, I think, more obvious recently. There's been a couple of papers that have come out. One individual, Sebastian Bacher, who I highly respect as a computational biologist and somebody who focuses in on mass spectrometry, tandem mass spectrometry type analysis, among other areas. He recently put this paper out, Small Molecule Machine Learning, All Models Are Wrong, Some May Not Even Be Useful. So, which was a fairly strong statement to say about the current state of where we are with respect to these in silico types of analyses. And another paper, this one came out this year, and this was a paper where they were using an orthogonal spectroscopic test to look at the structures of ions and compare those in silico-based annotations to what the spectroscopic test was telling them. And their statement was basically that there's virtually none of the fragment ions matched, the in silico-based structures matched the spectroscopic tests. So it's again, two very strong statements. And we ultimately, as said, over the course of 2 years since when we put this in there, back in this type of data into our database, we realized that the in silico data was highly erroneous. And since then, all in silico data in Metlin has been removed. So we do not rely on in silico data. And that's not to say that in the future it could be much improved, but the current state is that in silico data is not in Metlin, nor do we use it in any way at this point, simply because our experience has been fairly has not been very positive. So with that, the last of these 4 topics that we investigated was in silico fragmentation. I'm sorry, not in silico. I'm sorry, in-source fragmentation. So in-source fragmentation is a phenomenon, and we don't typically associate in-source fragmentation with electrospray ionization. And we know that electrospray, John Fenn won the Nobel Prize in 2002 for electrospray, and largely because it has been known to be such a soft ionization technology. When we typically think of electrospray in either positive or negative ionization mode, we typically think of it as being predominantly generating intact molecular ions, which is one of its real powers. And this is in contrast to electron ionization, which is a much harsher ionization technology. This has been around for over 70 years now, and where an electron beam passes through the sample. And predominantly, what you see with electron ionization is the in most cases no precursor ion generation at all, and pretty much everything, or the vast majority of what you typically see, is in-source fragmentation. So in-source fragmentation has been very well known to exist for over 70 years now. And ever since the advent of electrospray ionization, it certainly has been recognized as an event that occurs with electrospray. So what I'm about to show you is not anything new. This is not in-source fragmentation with respect to electrospray ionization. It's not a new phenomenon. It's something that many groups have noticed for decades now. It's a common phenomenon that occurs with electrospray. It just doesn't occur to the extent that you see with electron ionization. However, the potential issue with this is that when we do our LC-MS experiments, as in metabolomics and in lipidomics, we typically are generating MS-MS data on what we presume to be the molecular ion and any other peaks that are showing up. So any other peak showing up could also be the in-source fragment ion. So in this particular case, we would be getting not one MS-MS spectra, but in this case, 5 MS-MS spectra from the same molecule. Basically, these are the ones in red are not molecules; they're fragment ions, so they do not represent real molecules. And this term, phantom metabolites, was coined by Derek Lowe in a recent Science article that was in response to a paper that we have come out in Nature Metabolism. Just prior to his article coming out in response to ours. And he basically was saying that these fragments, that ions with the MS-MS data did not represent, and this is what the point of our paper was, that these fragment ions did not represent molecules, but they were in fact the phantom metabolites, or just more artifacts than anything else. So the question we asked with respect to this is, how prevalent is this in-source fragmentation? And that was the point of our Nature Metabolism paper, and that came out in June. The hidden impact of in-source fragmentation in metabolic and chemical mass spectrometry data interpretation. And so what we set out to do here was actually look at the prevalence, and I'm just going to show you a few examples, real-world examples of MS-MS data at 0 electron volts, which I mentioned we had in Metlin earlier, and how that compares to in-source fragmentation. In-source fragmentation, of course, is taking place in the source. The MS-MS data that we have here in Metlin is occurring at the inside the collision cell. But you can see there's actually a great deal of similarity here. For adenosine monophosphate, you can see the in-source. There's a little bit more in-source fragmentation than fragmentation we saw with MS-MS data. Here we have a couple of fragments. We have for the MS-MS, the in-source fragmentation is again the same fragment ions, but of slightly higher intensity. And this has actually been a fairly common phenomenon that we've observed across the board, that the in-source fragmentation tends to be slightly more energetic than the MS-MS at 0 electron volts. So the question is, how prevalent is this? So we actually looked within Metlin at our 930,000 plus molecules and at 0 electron volts to see how prevalent would the MS-MS data be at 0 electron volts, and by similarity, that should answer the question of how prevalent is in-source fragmentation. So what we found is that if you consider the molecular ion a particular peak, we found that in general, 70% of the peaks that we were observing were molecular fragment ions, and the molecular ion was also only constituted 30%. That's when we had a 5% threshold for the fragment ions. When we changed that to 3% or 1%, the number of fragment peaks jumped up to over 90%. So the prevalence of the fragments is actually quite high. And this was that prompted the article by Derek Lowe back in July of this year. So what this actually means, and for things like molecular networking, all of these nodes are presumed to be molecules that are based on MSMS data and similarity searching and in silico identification. If you take away 70% of those, basically the networking actually changes quite dramatically. So what is the overall message that I'm trying to make here? Well, the message is LCMS data is predominantly represented by ISF in source fragmentation, and therefore the metabolome lipidome are less complex than originally thought. So that's a very positive message. The message is that a lot of the the peaks that we're seeing do not represent new molecules, but instead they represent fragments of those molecules. So the complexity is much less, and that means the dark metabolome or the dark lipidome is much less complex as well. And those are primarily made up of these phantom metabolites. The solution is extremely simple. I think the solution is a solution that we can take from not just our platform, our XCMS and Metlin platform, is how do we ensure identification integrity and avoid characterizing molecules that don't exist. And basically what we've done is we do the same thing we've been doing all along. We use established criteria for identification. If we don't have solid data like accurate mass measurements, like tandem mass spectrometry data that matches and in-source matches the molecular standard, we simply don't use it. And that's kind of that's the very last thing I'm going to mention here, and that's our paper that just came out a couple of weeks ago in Molecular Systems Biology, which was the integration of XCMS and Metlin with the full database. What we are doing here is basically only identifying, and when I say identifying molecules, we're only trying to identify molecules that are solidly based on molecular standards. And if you're using other approaches like similarity searching or in silico based conjecture, you run a real risk of identifying molecules that don't exist. So again, the message is fairly simple. The metabolome lipidome, I think, is simpler than we probably thought, and that is true significantly so. And the solution is also very simple. We just rely on technologies that have proven, and it doesn't have to be XCMS and Metlin. It can be other technologies that exist out there that are also quite reliable. You can either from manufacturers or the online versions, but that's the primary message that I have there. And finally, I want to acknowledge Aries Ace-Porna, who has been largely involved in the informatic development of Metlin and XCMS, and also doing the analysis for the in-source fragmentation. Martin Gier, who we've been working with closely, and intellectually it's been very enjoyable and a lot of fun working with Martin and discussing all of these issues, because we both have found this area of all these extra peaks fairly fairly confounding, and hopefully we've come up with a reasonably good answer. Winnie, your tie is responsible for over 95% of the data that was generated, and the other, all of these studies involve Lynn and Corey and Elizabeth. So I thank you for your attention, and sorry I went over a little bit, but I fortunately didn't go over so much that I've totally run out of time, but probably I'll just have to answer offline the questions that have come up. But thank you very much.
Thank you very much, Gary. We do have time to answer, I guess, one question before you go. So what results have other approaches, for example, credentialing, come up with to address this question of complexity?
Yeah, the credentialing, that's a really interesting question, because the credentialing approach was an approach that is based on using isotopically providing cells with an isotopically labeled medium, and using that information to get a better sense of what were real molecules or real metabolites or lipids in these systems. The most recent assessment that they performed on and published on this was in JACS a couple of years ago, and they came up with fragmentation as only being in the single percentage level, like on less than, I believe it was less than 5% of the peaks were associated with in-source fragmentation. So our results are very different from what's been observed with credentialing. So the only thing I can think of that is different between our approach and their approach is that perhaps they use different thresholds and just had a much higher threshold for observation than we did. And our 5% and 3% and 1% thresholds, I think, allow us to see and get a really good representation of the in-source fragments. And it should also be noted that we typically do these experiments. We have a dynamic range of anywhere from 5,000 counts in intensity to 1 million counts of intensity. So looking at 5% and 3% of the height of a peak is very reasonable in terms of a reasonable dynamic range. But thank you.
Thank you very much, Gary. Unfortunately, that is all the time that we have for today. Like mentioned already, any remaining questions we didn't get the chance to address will be forwarded to the speaker after the event. So like all the talks in this event, today's session will also be available for on-demand viewing for the next 30 days. Once again, thank you, Gary, and thank you all for joining. We'll be back tomorrow at 8 a.m. Pacific with another exciting lineup of talks. Goodbye.